Regents review 1, kinematics and force. All right, so I figured I'd record some videos here because we're going to go through them pretty quick in class. That way you can use these to study for various review quizzes. So let's get going. Which quantities are scalar? So scalar quantities don't have a direction associated with them. They're just a quantity, a size, magnitude, a value. Speed and work, those instantly look like scalars to me. Velocity has a vector, force has a vector, distance is a scalar, acceleration is a vector though. Momentum is a vector, power is a scalar. So the only two that are both scalars are speed and work, right? Work, it can be positive or negative, but that just means it's kinetic energy is going up or down. All right, number 2, 3 kilogram mass is thrown vertically upward with an initial speed of 9.8 meters per second. What is the maximum height this object will reach? All right, so it's important to realize all right, so again, let me start that over. 3 kilogram mass is thrown vertically upward with initial speed of 9.8 meters per second. What is the maximum height this object will reach? All right, so this is kinematics. You're throwing it vertically upwards. V initial is 9.8 meters per second. V final is going to be 0 because it's at the peak. Acceleration is negative 9.8 meters per second squared. We're looking for the height, so delta y, we'll call that. So I don't know anything about the time. This looks like classic V squared equation. So V final squared equals V initial squared plus 2a delta y. All right, V final is 0, so we can eliminate that. So we're looking for delta y. So delta y would equal, you bring that over there, so it's negative V initial squared divided by twice the acceleration, so negative 9.8 squared over 2 times negative 9.8. They did that on purpose, so the math could be pretty simple. One of these gets canceled, one of these gets canceled, negative sign gets canceled, you get 4.9 meters, so 9.8 divided by 2 is 4.9 meters. It's a nice little kinematics question to warm up there, that V squared equation. You'll be able to get that off your reference table. It'd be great. All right, a 160 kilogram space vehicle is traveling along a straight line at a constant speed of 800 meters per second. The magnitude of the net force on the space vehicle is 0. A equals F net over M. Since it's a constant speed, V is constant, so the acceleration is 0. And therefore the net force must be 0. Very good. Student throws a 5 Newton ball straight up. What is the net force on the ball at its maximum height? This is a trick question. You got to realize when something's in projectile motion, the FG is always acting, right? Whether it's an arced path, a vertical path. So even though it's got a velocity initial, V here is 0 at the peak. The net force is just mg, so it's 5.0 newtons, and it's directed down. It's directed down the whole time. Now that's one that you could overthink, right? It would have been mean if they had put 50 newtons as one of the answers, because that would have been, a lot of people will just take that and automatically multiply it by G. But you got to realize it doesn't say with a weight of 5 newtons. It just says a 5 Newton ball. So it's up to you to realize that that's the weight, not the mass. All right, this one here, this is a little different one this year. This one here, it's traveling north at 220 meters per second and encounters a 50 meter per second crosswind from west to east. What is the resultant speed of the plane? So this is vector addition. or finding the resultant. It's traveling this way at 220. Yes, I'm just redrawing these vectors, but I'm drawing them like this, 50 meters per second. The resultant velocity, this is like the y component, this is the x component. So the resultant velocity is the square root of 50 squared plus 220 squared. So get out my calculator. It's the first one I've needed the calculator for. All right, second square root, oops, better clear my calculator first. Second square root of 50 squared plus 220 squared is 225.6, so 226 meters per second. And this is one where these two you could eliminate right away because the resultant always has to be bigger than the two components. So, you know, it's just the resultant vector, whatever. That could be a force, velocity, acceleration, you name it. But anyhow, vertical spring has a spring constant of 100 newtons per meter. When an object is attached to the bottom of the spring changes from 0.5 to 0.65. Okay, so classic Hooke's law problem. All right, starts out here at 0.50. It stretches to 0.65 meters. So the x here, the delta x at force of spring equals kx. So the x here, I guess we don't need the delta, is 0.15 meters. The force pulling it is the force of gravity, which is what we're looking for. K is 100 newtons per meter. So the spring force would be 100 times 0.15. That's going to be 15 newtons. And we must be in equilibrium because it stretches and stops falling down. So the spring force has to equal the force of gravity. So boom, 15 newtons the spring force must support. Hooke's law, don't forget about that one. That one's in the mechanics section. A 1.5 kilogram cart initially moves at 2 meters per second, is brought to rest by a constant net force in 0.3 seconds. What's the magnitude of the net force? All right, so F net equals MA. We got to find A first. So it's A is delta V over T. So we're losing 2.0 meters per second in 0.30 seconds. So let's just get that number quick. 2 divided by 0.3 is negative 6.7 meters per second squared. Then I can take that up here. Now remember, on your reference table, it gives you A equals F net over M, which we often rearrange to F net equals MA. So we've got 1.5 kilograms times 6.7 meters per second squared. We don't need to worry about the negative sign because it's asking for magnitude. So I get about 10 newtons. Pretty straightforward question, just Newton's second law and kinematics. All right, on to the next page here. I'd like to get some conceptual questions here. We hit a lot of calculations here early. As a 5.0 times 10 to the 2 Newton basketball player jumps from the floor towards the basket, the magnitude of the force on her feet is 10 to the 3rd newtons. As she jumps, the magnitude of force on the floor on her feet is, well, let's draw a force diagram. We've got Fn. That's 1.0 times 10 to the 3rd newtons. That's how much force she's pushing down on the floor. And her gravity is 5.0 times 10 to the 2 newtons. I guess I've answered this question without really, I should have just thought about it to begin with, but this is classic Newton's third law. The magnitude of the force of her feet on the floor is that the force of the floor on her feet has to be the same and opposite. All right? That's what propels her upwards. While we're over here, let's go over to this one, which diagram best represents the position of a ball at equal time intervals as it falls freely from rest. The dot's got to get farther apart. So this is where it's starting, V0 up here, and they're falling this way. That's a little bit confusing the way this is drawn, right? So the dot's got to get farther apart as it falls, just like our video analysis program. 33, a different force is applied to each of 4 different blocks on a frictionless horizontal surface, in which diagrams the block have the greatest inertia 2 seconds after starting from rest. Inertia equals mass. Please, look at all this setup. All right? Look at all this setup. They give this nice big diagram. They're just trying to fool you. It's this one. Don't even think about it. It's just whatever mass is biggest. Don't overthink that one. Ooh, we love these ones. The diameter of an automobile tire is closest to. Kids are always like, what the heck? How are we supposed to do that? All right, well, a car tire. Okay, it's about 1/2 meter, maybe at the most, right? 1/2 meter or so. So about 0.5 meters. So this is really all about figuring out which of these makes any sense at all. So this is 10 to the 1 is 10 meters. 10 to the 2 is 100 meters. Clearly those can't be it. Way too big. 10 to the negative 2 meters. All right, let's write that in decimal form. 10, 1, 2. That would be 0.1 meters. That would be 10 centimeters. All right, that's not big enough at all. 10 to the 0 would be about 1 meter. Yes, a meter would be a really big tire. That'd be like a monster truck or something, like a big old truck. But it's the closest. It says closest. It's really about the exponent here. It's really about the exponent of the power being the closest. No, 10 to the negative 2 is even smaller. What am I talking about? But anyway. A car tire traveling at 15 meters per second. So it's, yeah, it'd be 1 times 10 to the negative 2. So it'd be 0.01. 0.01 meters, which would be 1.0 centimeters. Holy cow. All right. Anyway, a car initially traveling at 15 meters per second north accelerates to 25 meters per second north in 4 seconds. The magnitude of the acceleration is A equals delta V over T. Not sure what they're getting at here. It's from north to north, so it's going this way to this way, so it's gaining 10 meters per second in 4.0 seconds. So that's 2.5, straightforward. I don't know, pretty straightforward. I don't know what their other earlier one was more difficult than that one. All right, car moving at constant speed of 20 meters per second. What's the total distance the car travels in 2 minutes? It's just about distance equals average velocity times time, or I guess we usually say delta x equals average velocity times time. Since it's constant, you use 20 meters per second. The key is 2 minutes you have to convert, right? 2 minutes times 60 seconds per minute, right? So 40 times, it should be 40 times 60, which gives us 2,400 meters. You know, they could put kilometers as the answer, so that'd be 2.4 kilometers. They could do something like that to try to make that a little bit harder. All right, on to the next one. Getting there. The vector diagram below represents the velocity of a car traveling at 24 meters per second, 35 degrees east of north. Okay, what is the magnitude of the component of the car's velocity is directed eastward? So it's just the x component. That's this component. Now there's multiple ways you can do this. I'm going to use sine here, or you could solve for that angle, right? That'd have to be 55 degrees, right? A lot of you like to do that. So you could say Vx is, this is 24 meters per second. So you could do 24 meters per second times the sine of 35 degrees, or Vx equals 24 meters per second times the cos of 55 degrees. Whatever way you want to do it, whatever way makes sense to you. I know a lot of you like to always use cos with x, so you know, I understand that. So you can do that. You just gotta subtract from 90 there. 24, great. There's a weed eater going out there now. I get 14 meters per second, and then just to be thorough, we'll do both of them. We get 14 meters per second. So confident in our answer there. Without air resistance, a kickball would reach a maximum height of 6.7 meters and land 38 meters away. With air resistance, the ball would travel, all right, it can't travel as high or as far. So we're looking for, now this is where reading gets hard, right? You know, making sure you're less and less. Vertically and more than no. Horizontally, no, it can't go the same distance horizontally. It's not gonna go higher either. So 4, less horizontally and less vertically. That one's a pain, that was annoying. An object in equilibrium, which force vector diagram could represent the forces acting? You gotta make sure everything's balanced. Clearly that one's no good. This one's balanced left to right, but not up and down, so that's not it. This one's down is bigger, that's not it. This one, left to right, you gotta think about components, right? So that one balances left to right, and then their y components would add together, right? And it would balance, so it's that one. I like that one. That one is pretty straightforward page. Okay, we're on to the short answer questions here. Football is thrown at an angle of 30 degrees above the horizontal. The magnitude of the horizontal component of the ball's initial velocity is 13 meters per second. The magnitude of the vertical component of the ball's velocity is 7.5 meters per second. On the axis in your exam booklet, draw a graph representing the relationship between the horizontal displacement of the ball and the time of the football is in the air. All right. Projectile motion, classic. Remember, the key here is, this is really, I meant to do this on the next review sheet. I should have put this on. Whoops. But I'll do it now and then I'll probably do it again. AX is 0. AY is negative 9.8 meters per second. So we're in a constant velocity. Constant Vx, right? Vx, Vy. Vy at the peak is going to be 0, but Vx doesn't change. Vx is constant and hits the ground going fast. So displacement versus time for this has to be linear, all right? Because the x velocity is constant. Football is caught at the same height from which it's thrown. Calculate the total time was in the air. 2 points. So that means that since it's caught at the same height which it was thrown, that means delta y is 0. All right, we're looking for the time of flight. The initial y is 7.5 meters per second. AY is negative 9.8 meters per second squared. I really should have put this on the next packet. I'm gonna have to go and edit this file for next time. Anyway, AY equals negative 9.8 meters per second squared. So I'm gonna use El Grande. Delta y equals 1/2 AYT squared plus V initial YT. We're looking for the time of flight here. Now this is interesting. 0 equals 1/2 of negative 9.8. I listed the variables with units here so that I don't have to put them in here. That's just gonna make things messy. All right, we're solving for t, so bring that over to that side. We're gonna have 4.9 t squared equals 7.5 t. One of the t's cancels. We're gonna get t equals 7.5 over 4.9. All right, this is worth 2 points. Again, I should have put this in the next video, but on the next worksheet, I don't have time to reprint this thing, but maybe I'll just eliminate it from contention today. 1.5 seconds, worth 2 points. All right. Diagram below represents a 4 Newton force applied to a 0.2 kilogram copper block standing right. Oh, I do need my reference table. Darn it. Hey, Bannon, can you look up physics reference table for me? I need the coefficient of friction between block and steel. All right, determine the weight of the block. Well, Fg equals mg. All right, 0.200 kilograms. Hey, look at this. Look at this guy. Fresh from Mr. Coulomb here. Coefficients of friction. All right, thank you. Times, you can use 10 here, you can use 9.8. We use 9.8 just to be thorough. So 0.2 times 9.8, one of the easiest calculations in physics, but, and look at the two sig figs, it's 2.0. It's 2.0 newtons, the kilograms cancel. 2 points for that, people, come on. You don't want to lose those points. Calculate the magnitude of force of friction on the block. Force of friction equals mu, oh no, that's only 1 point, so you didn't even have to show this work. Literally, they'll give you a line with the units there, and you literally just put the 2.0 on the line. Mu Fn, all right? This seems like it's two equations, but your normal force is this, right? It's gonna be that 2.0 newtons. Coefficient of friction, it's sliding, so we gotta use copper on steel, kinetic, 0.36, very good. Thank you there, Mr. Bannon. Again, 0.36 times 2.0 newtons. 0.36 times 2 is 0.72. So the force of friction is 0.72 newtons. Okay, so this problem continues. It's a beauty. I love this problem, so I better keep this nearby here. Keep this up there. We want to know determine the magnitude of the net force acting on the moving block. So F net. Now, here's the deal. Let's look at a force diagram. We have Fn, right? We've got Fg. Those are balanced. We've got a 4 Newton force pulling this way, and we've got a 0.72 Newton force pulling back that way. So normal force and gravity cancel. We just got to find the difference between these two forces. So it's 4.0 newtons minus 0.72 newtons. F net is going to be about 3.28, I guess. 4.0 minus 0.72. Don't want to make any mistakes. You could round it to 3.3 newtons. That's fine. And that would be another one where it's like they just give you a blank line and then the unit, you just got to put the number on it. 3.3, that's all you write. Fine. Describe what happens to the magnitude of the velocity of the block as the block slides across the table. It would go up. You don't need to say any more than that, but the reason is A equals F net over M, and we have an acceleration. All right, it doesn't say why. It doesn't say why, it just says describe what happens. All right, so no why, it's just what. All right, that's it.